Okay, so again, good morning, everyone. This is the second part of the HEC RAS virtual training. And today we are going to see more in details other characteristic of the RAS and in particular how to perform some hydraulic simulations. So let me share my screen. Okay, before starting seeing new elements, new feature of the RAS, I would like to show this little summary, uh, which is a summary of all the steps that the user must do in order to develop an hydraulic model. There are essentially 5 main steps. Yesterday we saw the first 2, how to start a new project, then how to enter all the geometric data needed. And today we are going to focus how to enter the flow data and the boundary conditions, then how to perform the hydraulic calculations, and at the end, how to view the results of this of the model we worked on. So just to make it more clear, every steps, starting a new project is what we learned yesterday. From the main menu of the RAS, a new project can be created. Then you can work on the project, creating all the other files needed for the hydraulic simulation. The second step is to define the geometry of the river system that you want to use for the hydraulic simulation. So there are many tools and features, some basic and some advanced feature, but the necessary ones are for sure the river, the ridge, and then a definition of the cross section. We saw this yesterday. If you have any question about this, you can just ask. If something was not clear from yesterday, just let me know. We can try to discuss and make it more clear. Otherwise, we are going to see the next steps for making a simulation, which is entering the flow data and the boundary condition, which determine the simulation, the hydraulic simulation you are gonna do. These steps is a little bit different if you are performing a steady flow analysis or an unsteady flow analysis. And I just want to remember that the steady flow case is when you have a variable geometry, so the river changes its shape along its path, but you simulate a constant flow. While the unsteady flow regime is the most general case in which you have a variable geometry, so a river which changes its shape along the path, and also the flow simulated in the river system is changing during the time. So the unsteady flow analysis can be used to simulate an hydraulic event that lasts days, months, or time period you want, with a flow that changes during the time. Once you have entered all the flow data and the boundary condition needed, the next step is to perform the hydraulic computation, and also in this case, the procedure is a little bit different from a steady flow analysis or unsteady flow analysis, but essentially the user has to insert all the options to describe the computation that the software will do. And these 2 things, how to insert the data, the boundary condition, and how to perform the hydraulic computation is the main topic of today, because at the end, when you create a simulation, your last purpose is viewing the results that you obtain in the river system that you have schematized, and the results can be seen both in graphic format, for example, uh, looking at water surface at cross section. Sorry, maybe I can go into and no. Okay, so maybe it's visible for you. The results I was saying can be seen all both in a graphic format, for example, checking at the specific cross section, which is the water surface, which are the parts involved in flow, or you can also check the profile of the reaches and see the profile connected to a specific time of the simulation. So there is a new person. Okay. Sorry, there was a question in the chat now. What I did not understand yesterday was how to generate rating curve. We're brief on it yesterday. Okay, generate a rating curve, Lucky. Now I try to answer your question. It's not so easy. It's a good question, but to generate a rating curve, you need to have um, many information about the river you are studying. You must have, for example, uh, observed the stage level and observed the flow data. And if you have enough information about the river, you can try to realize a rating curve, but it's not a binary condition that can be made so easily. You need to know the river system, you need to know what happened during a flood event, and you can combine different information you have, both about the level and both about the flow, and you can update this rating curve that can be inserted in the RAS. I hope I answered your question, but yeah, it would be a very big discussion about this topic, and I do not want to enter too much in hydraulic details and technical analysis. Let's say for now in this course. Did I somehow answer your question, Luki? Okay, thank you. Okay, let's go back to this presentation. Okay, so what I was saying that the purpose of creating an hydraulic model is then check value of water surface, value of flow that are involved in our river system, that can be seen both in this graphical format, but then you can check the results also in a more detailed way through some tables with a summary of many hydraulic properties computed for all the cross-section reaches. You can decide which results you want to obtain in the simulation file, and we are going to see it. Or if you are working with a bidimensional hydraulic model, you can also see the results through some maps. Okay, this is a little summary of what are the steps during a simulation and what is our final purpose in creating an hydraulic model. Now, let's try to analyze first how the steady flow analysis should be led. So, if you remember, for the steady flow, you need to create a steady flow file which contains the flow data and the boundary condition. This file can be created selecting from the main menu this button, which is the steady flow analysis. And from here, you will see this window. Here, let's have a look a little bit more in detail. Just remember that the steady flow case is a flow case in which the flow is constant. So for each river, if you fix a flow, you will obtain a profile which describes how the stage change along the river. Doing some steady flow analysis, you can use multiple, sorry, it's not working, okay. In a steady flow analysis, you can consider different flow in the same time in a simulation. So for example, if you put that you want to compute two profiles, then you will have to enter two different values of flow. In this case, these two. Here, this value is entered in the cubic meter per second if you're using the metric system. And so this is the flow data needed for the simulation. It is also possible to add some flow change location in the same reach. Just add a new river station. This is useful, for example, if in your river system you have more than one reach. For example, you have a main river and one or more tributary that join the main river, and so you take account of the flow coming also from the tributary, and so you can specify the water changed in some specific location. For example, it can increase if a tributary is joining the river, or the flow can also decrease if a tributary or a channel is splitting apart. So this is about the flow data. Then you have to enter the boundary condition. Now I do not want to enter too much in hydraulic analysis, but there are three kind of regime that can be computed. If you choose to perform a supercritical flow, then the boundary condition needed is the one upstream. If you choose to perform a subcritical flow, then the boundary condition needed is the one downstream. If you perform a mixed flow, you will need both a condition upstream and downstream. And now let's see briefly what the boundary condition types are, because the user can choose from different boundary condition type. So the first option is using a known water level. This means that if you know the value of the water surface at a specific cross-section for a specific profile, you can enter this value, and in this way, the program will not compute a water surface elevation for that specific cross-section. It will use this known value and then move the computation to the next sections. Another option is to use a critical depth. The critical depth is a hydraulic characteristics that only depends on the physical characteristics of the system. So once you have defined the geometry, the program will automatically compute the critical depth. And so when you select this type of boundary condition, you do not have to enter any other further information. You just have to specify you want to use the critical depth. And this is a boundary condition that usually is applied at the downstream cross-section. Then another option is to use the normal depth as a boundary condition. In this case, what is the normal depth? The normal depth is a characteristic calculated with the energy slope. And the energy slope, it's not a data so easily to have, but it can be in general approximated by using the average slope of the channel in the vicinity of the cross-section. While the last option is the rating curve that we just mentioned before. So the user must enter a combination of elevation versus flow, and the program will use this condition to interpolating this rating curve, and will computation for the calculation needed for the simulation. Let me stop a little bit. Is this clear, or let me check if you have any questions. Okay, so that was the basic information you need to know to create a steady flow file which contains the flow data and the boundary condition. Once you have done this, you have to create a plan. A plan is the file which contains all the information that define the simulation. So by clicking on this button, you can open the steady flow analysis editor. Okay, and with this file, you can select which geometry file to use, which steady flow file to use, because in a project you can have at the same time multiple flow file, multiple geometry file. So when you create a plan, you essentially create a pack in which you specify which geometry and which steady flow file have to be used. And then you have to decide which flow regime to use. Okay, now I put this slide, but I do not want to be too much specific, and with hydraulic formula and equations. Just be aware that if you perform a subcritical flow regime, the calculation will be done from the program from downstream to upstream. So this is why if you select the subcritical flow regime, you need a boundary condition downstream, because it's from here that the program will start the computation, and so you need some value to start from. While the supercritical flow regime is somehow the opposite, the calculation starts from upstream and goes in downstream direction. And so that's why you need to to have a boundary condition imposed in the system at the upstream cross-section. The threshold, let's say, that divide the supercritical and subcritical regime is the critical condition, which is a characteristic that depends on the geometric data of the system and can be computed if you have at the same time both the condition. In this case, the mixed flow regime is the best choice, and the program will calculate both the profile with a subcritical hypothesis and both in a supercritical hypothesis, and then with a balance of forcing the program is we will get the final profile, which is more accurate if you have some transition between the subcritical and the supercritical analysis. Maybe everything explained like this can be not so clear, so let's try to move to one exercise and let's try to create all this file and to do a simulation. So probably it will be much clearer for you. Okay, see one notes. Okay, on boundary condition, you mentioned that critical depth can be applied on downstream. My question is which boundary condition can apply on upstream while developing a model? Okay, let's say that the program will help you. What I mean, when you select a cell, both upstream and downstream, it will automatically highlight which boundary condition you can use and which you can't use. Upstream, you can use also the normal depth can be used, the critical depth, but the program will show you which are the option allowed and which are not. Now we can see also in the exercise how it works. So let me open. You can also prepare in the training material we shared and go to the exercise free folder. And here there is both the solution in which there are all the files with the performed analysis and the geometry file, the steady flow file already let's say finished and ready with the solution. But in the exercise folder, you will find the project file we will start from. So first, let me open this. Okay, and close this one. Open RAS software. Let me open the 6.6 version as probably the version you have. Okay, and for now I'll keep here. Let me open the project. You have to look for the path where you located the folder with the training material and select from here exercise 3. From the exercise folder, there is a project called Critical Creek. Just select this one. Okay, and you will see there is already a geometry file set in this project. Okay, I will give you some time to look for the project and open it. Okay, let's say first that this exercise is an example taken from the application guide, which you can find on the RAS website. If you want to check more in detail, it's available online. It's just in this example, I just convert the unit system, which was the customary, the US customary, into the international system. So maybe the value and the units are different, but the example is actually the same. And the purpose of this example is to perform a basic flow analysis on a single river reach. And with this example, we will see also some warnings, some need of changing in the geometry that can occur when you create a simulation. So for example, we are going to perform a steady flow analysis in subcritical regime. Then we are going to check the results, and we are going to improve the geometry in order to obtain some better results. Then we are going to perform again a steady flow analysis, this case in a mixed flow regime, and check if this changing were useful to obtain better results or not. So yes, let's open the project. If you haven't done yet, just from the file menu, select open project. You have to go to the directory in which you saved the folder exercise 3 and select the project called Critical Creek. And that's what I've done. Now let's have a look at this geometry data present in this project. So from the main menu, click the View Edit Geometric Data button, and you will see there is in this geometry there is one river. This one is called Critical Creek, and it's one single ridge called Upper Ridge. Then you can see there are 12 cross sections, and in this case, as you can see, the cross section river station is just a number. It's not actual river stationing. It's just a value number that has been entered in order to put the cross section in order within this ridge. Because if you go to tables, ridge length, here you can see which are the distances, the real distances between the cross section along the channel and the left and right overbank. And as you can see, the average distance between two consecutive cross sections is about 150 meters. Then another important information you can look at is from the main menu. If you click this button, the View Profiles, you will be able to see which is the profile of this geometry. Here you see that every black dot is essentially one of the cross section present in the model. If you click in one of them, you will be able to see both the river station and the elevation of the invert elevation of this cross section. So the minimum elevation that this cross section has. For example, the cross section downstream has a minimum elevation of 532 meters, while the elevation, the most upstream cross section, is 539 meters. So there is a change of more or less 15 meters along the river, and this river is approximately 1,700 meters. This means that the average slope of the river is about 1%. You can also check the average of the river. If you click the Control key from the keyboard, you will have this tool which allow you to draw a line and so some general measure properties. So for example, the delta x, delta y, and this duration. So essentially is the slope of this ridge 0.01, which is 1%, 1% slope along this river. These characteristics, the river can be considered a steep slope ridge. Okay, then let's check if the geometry is ready for the computation. So the other information that must be entered for sure in a geometry are the roughness coefficient. So from the tables menu, you can look at the meanings by clicking on this. Okay, you can see that different coefficient have been set for all cross-section in the main channel and in the overbanks. So the geometry is fine. We have a river, ridge, we have a cross-section with all the information needed. We can start creating a steady flow simulation. So as we said before, we need to enter the flow data and the boundary condition in a steady flow file. In this case, in this exercise, we want to simulate an hydraulic event with a return period of 100 years. And we know that for this kind of event, Creek River has a flow of 255 cubic meter per second at the upstream cross-section, so at cross-section 12. But then the flow increased to 270 at cross-section 8 because there is a tributary that joins the main reach in that cross-section. So essentially, imagine we are going to specify a flow which comes here from the upstream, and then here in proximity of the cross-section 8, just imagine there is another tributary which join the river, and so we have to take account of the flow coming from this other river. Let me admit other people which are joining. Okay. Okay, so the first step, we want to enter this flow data. We need to open the steady flow file editor. You just have to click this button, the one next to the geometry window, and this in this window we can enter this flow data. In this case, it's okay. We want to create only one profile, which is the profile of the event with a return period of 100 years. Automatically, as you can see, there is selected the upper cross section, the cross section with river station 12, because it's here that we have to specify the flow data. But as we said, we also want to specify the flow data in cross section 8. So in order to do this, you have to select with this drawdown menu the cross section you want to set. So in this case, we only have one ridge and only one river, so that's okay. We just have to select from river station number 8, and then click to add a flow change location. Okay, in this way you will have a cell in which you can insert also the flow data for the cross section 8. So let's specify for the cross section 12, 255 and 270 for the cross section 8. Okay, this is our flow data. From the option menu, you can edit the profile names, so you will be able to recognize this profile in the future. So let's change the profile name into RP100. So it's the 100 return period profile. Confirm, and now here you can see the name has changed. So you know that this column is referred to the profile called RP100. Okay, if you did these passages, you should have obtained this situation. And the next step is to enter the boundary condition. The boundary condition can be entered from this window. In this case, we have to click this button, reach boundary condition. When you do this, this other window will open, and here you can set the boundary condition upstream or downstream. In this case, we want to perform a subcritical flow analysis, and so we need a condition downstream. So you have to select the downstream cell, and in this case, we are going to use the normal depth. As I said, the normal depth is referred to the energy line slope that develop along the river, and which can be generally approximated with the average slope of the channel near the end of the river system. And as we saw from the profile, the average slope of this ridge is about 0.01. So let's set this value as a normal depth for this river. confirm, and you will see in the cell the description of the boundary condition you set. Okay, have you done this? Have you set this boundary condition, or there are any problems? Okay, if everything is okay, you can confirm this, and then you have to save this steady flow data. From the file menu, you can select Save Flow Data As and just put as a name RP100 profile. File. Okay. So if you create multiple profiles, it will be easy to recognize which profile is it. Okay, so we have saved. You can see also the name here at the top of the window now. You can see the name of the profile here. Okay, everything is now okay. We can close this window, and the next step now is to create the plan in order to do the simulation. To create a plan for a steady flow analysis, you have to select this button, and when you select this is the steady flow analysis editor. Just make sure that the geometry file selected is the right one, as well as the steady flow file. In this case, we have only one, so it's okay like this. We want to perform a subcritical flow regime, so it's okay this option. We just want to add one option. We want to plot at all the location the critical depth on the profile, so we can then analyze the results and see if the subcritical analysis was correct or not, because the critical depth is the discriminant to understand if the simulation should be computed as subcritical or if a mixed flow analysis is necessary. Because if the computed depth is below the critical depth, then the subcritical analysis is not completely correct, and maybe the model solution will not be stable and accurate. So from the option menu, you can select the critical depth output location and check this option. And confirm. Okay, so we added this option that will be useful when we look at the results. We select the right geometry file, we select the right geometry file, we have set also the flow regime, so we can save this plan like this. From the file menu, you can select Save Plan As, and you have to give a title to this plan. Let's call it subcritical. and confirm. Also, a short ID is required because in the title you can also insert a description. It can be a much longer title, while this is the short one. In this case, it's okay to put the same recap. The name would be visible here in the plan row, while the short ID will be seen here. And as you can see here, it's much shorter, while here you can also put a much longer name. And if you have multiple plan, from here you can open plan and you will see a list with the title, here is visible the short ID. So it's useful to put an ID which is uh, easy recognizable. Okay, so we have create the plan, it's saved, and so we can now compute. From this window, you can click on compute and the steady flow simulation will run. Okay, in this case it was a very short simulation, so it's already done and finished. If any errors occur, you will see the error written here in this window. It will be visible. There are some computation summary. You can see, for example, the time this simulation takes. In this case, it's very, very short one, so just take 1 second. When you perform, in particular, the unsteady flow analysis, it can be much longer, depending also on the time interval you are simulating. So let's close this one. There are no error in this case, but let's check the results. The first thing we can do is, first of all, did you try? Did you compute? Did you get any error, or the computation was okay? Someone of you managed to compute the simulation? Okay, if you had any problems, maybe then in the folder, in the training materials, there is also the solution with the project, with all the files needed to do the simulation, and also with the simulation already computed. And if you have any doubt, maybe later next day you can check this. You can check that project and compare maybe the one you are working on now with that one, and see what differences are there, what the problems may have been. So now we have done one computation, and we want to check the results, what we get from this simulation. So one way to check the result is, for example, by plotting the computed profile. The profile can be computed using this button. You can see here in the top toolbar, the main menu. This one is the profile button. If you click this, the profile of the reach will appear. You can plot different variables from options variable. You can select which one you want to see on the plot. In this case, it's okay. Like this, we see the water surface level as well as the ground, and then the critical line and the energy line. It's interesting to notice that the water surface level and the critical depth are in some of the location really close each other. Like here, the water surface is pretty close to the critical one, as well as in this portion of the reach. And keep in mind that we performed the analysis with a subcritical regime, and the hypothesis of the subcritical regime is that the water surface is always higher than the critical one. So if there are some parts like these, maybe we can evaluate to use a mixed flow regime. But first, I want to show you that you can also zoom from the option menu. If you select zoom in, you can select the area you want to see more in detail, and then with the shift key of the keyboard, you can move, or you can zoom out, or select the pen and move through the reach. So you can see there is some locations along the reach in which the water surface is pretty close or equal to the critical one. So we can check better the results looking also at with the detailed output tables, which can be opened with this button here. Here you will see a summary and eventual warnings, error, and notes for each of the cross-section in the system. So for example, here you can see now it's automatically selected the cross-section 12, and here there are many values obtained from the calculation. You can check, for example, the velocity, the water surface, which is the critical water surface, the flow, and so on. There are many variables. At this moment, the most important things is here in the error and warning notes box located in the bottom part of this window. And as you can see, there are two warnings. You can easily recognize the warnings because they are highlighted with a yellow color. Any error would be red, while the nodes will be green. Okay, so let's have a look to this warning. For example, for the river station 12, we have two. The first one says that the velocity head has changed more than 0.15 meters, and this may indicate the need for additional cross-section. Okay, we are looking at the cross-section 12, and keep in mind that for a subcritical flow analysis, the program starts the computation from downstream to upstream. So the changing of velocity more than 0.5 meters occurred between the cross-section 12, no, sorry, for the cross-section 11 and 12. And such a large change in velocity head might be due to, for example, a significant change in the cross-section shape. So if you have a big expansion or contraction of the flow, or a significant change in the slope. And so the program suggests you to add more cross-section, because in this case the significant change will be reduced, and this can lead to a more accurate surface profile. The second warning is somehow similar. In this case, the energy loss differences between the two cross-section was pretty high. And also in this case, the program suggests to add additional cross-sections. From here, then you can move and see all the other cross-section. As you can see, there are many warnings for each cross-section. You can check at all the warnings also from the view menu. There is this summary error warning notes, and here there is a window where you can see all the error warning and notes condensed in only one place, and from here you can check all the warnings that occurred during the simulation. So let's see other warnings that appear in this simulation. For example, this one, the energy equation could not be balanced within the specific number of iterations. The program used critical depth for water surface and continued on with calculation. In this case, this warning is telling us that the energy balance was not able to obtain a result in the subcritical hypothesis, and so the critical depth was adopted in that cross-section. Something similar is also this one. During the standard step iterations, when the assumed water surface was set equal to critical depth, the calculated water surface came back below critical depth. This indicates that there is no valid subcritical answer. The program defaulted to critical depth. And these are warnings that is saying again that the subcritical flow analysis was not sufficient. In this case, there was no solution in this hypothesis, and so the program used the critical depth and go on with the computation. So all these warnings are suggesting us that the subcritical regime maybe was not completely true, and maybe it's better to perform the simulation in a mixed flow regime, so we will be able to obtain a more accurate profile in that location where the water surface level is close or equal to the critical one. So in this portion and this portion, the profile that now we computed can be not realistic. There is another warnings. In this case, it's pretty different from the other ones. This one said that divided flow computed for this cross-section. This warning is related to the cross-section 10, where you can see the name, cross-section 8, 10. here is the warning. Location, river, critical reach, upper reach, river station 10, and this is the profile in which this warning occurred. Divided flow. So let's have a look to the cross-section 10. Select the cross-section menu and move to the river station 10. Okay, as you can see, the cross-section 10, here there are essentially two different areas in the cross-section which are not connected to each other, and the program is warning you that the flow occurred in two areas divided, because in this case there is this vertical obstacle that makes the water flow to be split in two. The warnings just point out this issue, then the user can decide if this condition is realistic or not, or if it must be checked or not. Because all these are just warnings, they are not errors. The computation is done anyway and correctly, but are just some issues that maybe the user should check and evaluate better. So in this case, there is this vertical obstacle, and so the user should understand if it is correct that the water flow both on the right side and on the right side of this obstacle, or maybe if it's better to enter one of the options that we saw yesterday, like the levee or an effective flow area. Because here, as you can see, this is the main channel. You can recognize it because it's the part of cross-section between these two red dots. So this is the main channel, and if you want the water not to flow above uh, on the left side of this obstacle, you can, for example, put a levee here, and the water flow will occur only in the right side where is located the main channel. Otherwise, with an effective flow area, you put an effective flow area in this portion, the water will go here, will fill the area, but will not flow. It will have a velocity equal to zero. But it depends on, of course, on the real nature of this river. So for now, we can keep this warning like this. We actually don't know if it's not if it is correct or not, this assumption. This is another warnings. Let's go back to the error warning and notes plan. This is something maybe too much specific. I prefer maybe to go on for this, but just keep in mind that all these warning and notes are only intended to inform the user that there are potential problems in some cross section, but it's also important to know that you do not have to eliminate all the warning messages. Yeah, it can be useful, but it's up to the user to determine whether or not these warnings required to be fixed with some actions or not. And so there is a message. Let me check the chat. I'm trying to follow along, but it's hard because I did not attend yesterday's session. Please try to go slow in the next exercise. Okay, sure. I try to go very, very slow in with this and the next one. I try to focus more on all the steps. Okay. Did you manage to maybe do the follow since now, or did you have any problems also in computing this simulation? Because maybe if you have some problem, we can have a look, or otherwise you can try to open the project from the solution folder. And here there is the computation already done. Maybe from here you can try to check together these warnings and all these characteristics. So we have seen there are many warnings. Now we want to try to check some of them because many of them suggested to add additional cross-section, and this can be done with the RAS software. In general, to add more cross-section, you will need a topographic survey, which can provide you more information of new cross-section to insert in the model, but of course, not always is possible to obtain new data. And so in the RAS program, there is a tool that offers the user the possibility to make an interpolation between two existing cross-sections. This is, of course, only an assumption, and then the user should check the interpolated cross-section and check if they are suitable or not to schematize the real configuration of the river. So let's try now to create some new interpolated cross-section and see if all the warnings that suggested the additional cross-section will disappear or not. Okay, to interpolate the cross-section, you have to open the geometric data window, which can be opened by click on this button in the main menu. Is the third one, and with this you can open the geometric data editor. Here you can see your geometry, and these are our actual cross-section. They are 12. Now we want to increase the number of cross-section, creating some new interpolated ones between each of two consecutive cross-sections. To do this, you have to go from the tool menu and select cross-section interpolation, the first option, and then select within a ridge. This option, you will interpolate the cross-section in all the ridge you select. So in this case, here you can select which river and which ridge to make the interpolation in. We have only one ridge, so let's select this, and you have to select. This is here in my presentation. You can check the passages you have to do if you haven't done yet. And this is the menu that will open when you select within a ridge. From here, you can specify the maximum distance between the cross-section. We saw at the beginning of this exercise that the average distance between the cross-section was more or less 150 meters. So let's try, for example, to interpolate the cross-section in order to have a maximum distance of 50 meters. Okay, and click on Interpolate Cross-Sections. When you close this window, you will see all the new interpolated cross-section. You can easily recognize them because they are drawn with a light green, while the original cross-section are the ones in dark green. Now, let's have a look of how this interpolation has been made. So again, go to the Tools menu from cross-section interpolation, and in this case, select between two cross-sections. Okay, just a moment, I see there is a notification in the chat. Okay, the person want to enter in the group. Okay, well, okay, still no messages. Okay. Okay, I think there is one person who can't enter the meeting. Should have done. Okay, so if you go from Tools, cross-section interpolation, and in this case you select between two cross-section, you will see the interpolated cross-section between the two original one. The original cross-section are the one in black, while you can see displayed in gray, the interpolated ones. You can move with this arrow and see the interpolation between cross-section. You can also see at the same time from the geometric window which is the location of the cross-section you are looking at. As you can see, the interpolation try to keep the main channel connected from one section to the other. But if you look, for example, at the interpolation which has been made between these two cross-sections, which are the cross-section number 10 and 11, you can see that something strange happened, let's say, because here the main channel and the left overbank is correctly interpolated, while here on the right overbanks maybe there is something not completely correct, because you see in the upstream cross-section there is this vertical obstacle, it seems like a wall, something, and then there is another vertical obstacle also in the cross-section 10, which have a shape a little bit different, but these two profiles are probably the profile of the same object that developed along these two cross-sections. While the interpolated cross-section, as you can see, there is this obstacle that vanished on this along this line, and this other one that get lower through here until disappearing. But this interpolation does not seem really realistic, and so we want to make it again better. So let's proceed like this. You can delete this cross-section and use this command to draw the chord lines to create a better interpolation. With this command, you can draw some chord lines, and you should draw lines that connect a similar point from one cross-section to the other. So in this case, we want to make a better interpolation of this vertical obstacle. So the way to do this is, for example, to create a chord that connects the bottom point of this obstacle. You have to click near the bottom point, drag and release near the point you want to connect. So like this. And do the same also for the top point of this vertical obstacle. So connect this one with the top one here. Somehow it does not recognize the point. You have to be quite precise in selecting the point. So let's connect the two top points and the two bottom points of this vertical obstacle. So try to obtain something like this. This is important because now, if you set the maximum distance here equal to 50, so the same difference we set also before, and you click interpolate new cross-section, you see that now the interpolation is forced to follow these chord lines that we draw. Okay, I give you some times. Try to do this. You have to draw 4 chord lines. First of all, you need to delete the existing interpolated, which were wrong. Then, selecting this button, you can draw these 4 chord lines connecting the bottom and the top points of the vertical obstacle from one cross-section to the other. Then, if you set again 50 meter as a maximum distance here in the cell and click interpolate new cross-sections, you should obtain something like this. Okay, tell me if there are any problems. I don't know why Dr. Nahid has some problem in entering the meeting. I admit him, but probably he had some problem with the connection because he's still exiting and entering again and again. I do not see any questions. I hope you managed to create this new correct interpolation between the cross-section 10 and 11. If you have done, let's close this menu and save the geometry with a different name. So from the File menu, select Save Geometry Data As, and in this way we kept the original geometry and saved this one with a different name. So the original one was called Geometry Start. Let's call this one Geometry Start plus interpolated. So it's easy to understand that in this geometry file there is the geometry with the interpolated cross-section. Let's confirm. Okay, and now here's the name of the new geometry. So many of the warnings pointed out the necessity of additional cross-section. We have done this. And another issues that many of the warnings point out, it was that the subcritical analysis failed at some locations and that critical depth was sometimes adopted to improve the results is to try to use the mixed flow analysis. In this case, the program will compute the profile assuming both subcritical and supercritical hypotheses. And then it will obtain the correct one through a balance of pores. Okay. To perform the mixed flow analysis, we will need another boundary condition, not only downstream, but also upstream. So we need to create a new boundary condition file. So let's go to the steady flow analysis, which can be opened clicking on this button. You will we have first to change the steady flow analysis editor, so this one, the first button in the toolbar menu. This is the file of the previous profile we set. Now we want to create a new one, adding also the boundary condition upstream. So go to reach boundary condition. From here, you will be able to add a boundary condition also upstream. In this case, we will use the same boundary condition type, so also the normal depth, also upstream, and with the same value of 0.01, which is the average slope of the profile in the location. In this case, it was only one reach, and the average slope was quite similar both at the end and at the top of the reach. So we can use the same value. Okay, so now we have both the boundary condition needed upstream and downstream for the mixed flow regime. So let's confirm and save this file with another name. So from the file menu, you can select the save flow data as. I see one message in the chat. Okay, the profile I saw sent by Ryan. It seems okay. Sorry, I saw it just now. And let's see, Marnat. Okay, very good. You managed to to make the correct interpolation. Okay, that's correct. I'm glad you managed to do this. Thank you for the feedback, Ryan and Marnat. Sorry if I saw the message only now, but sometimes the notifications are not immediately. I don't know why. But thank you for the feedback. So now let's go back. We were saving this new steady flow file to perform the mixed flow analysis. So we have had a new reach boundary condition. We have had this upstream normal depth. Okay, and we want to save this steady flow file with another name, so we can keep in our project both the old one and this new one. So if from the file menu you select save flow data as, you can put a different name, and let's name this one like RP 100 profile. It's okay because it's still the profile of an event with a return period of 100 here. Let's just add the mixed flow, so we will recognize that this is the file we want to use to perform the mixed flow analysis. Okay, saved. So let's close the steady flow data editor. And now what we miss to perform the analysis is to create a new plan. So let's open the steady flow analysis using this button. Check the man running on a flat. Let's open it. In this case, we have multiple choice for the geometry, and both for the geometry and the steady flow file. So make sure that this time you select the geometry with the interpolated cross section, and as a steady flow file, make sure to select the one created for the mixed flow. Okay, once you have selected the correct files from this drop-down menu, select also the flow regime as mixed, and then you can save this plan. So from the file menu, you can select save plan as, and let's call this one mixed flow. Firm, and insert it also as a short name, mixed flow. Okay, now our plan is ready, and we can compute and see if everything is okay or if we have any errors. Okay, the computational is done. Also in this case, it's pretty fast. So it's a very simple geometry. It does not take much time to perform this computation. Okay, I just want to leave a little bit of time to perform this computation. See if some of you manage to do this. Okay, I see one message. Okay, this is the cross section with the vertical obstacle. And probably you are wondering why we have still water both on the left and the right, or because we actually do not insert any levee or ineffective flow area. We just make sure that the profile of the interpolated cross section were coherent from the upstream and the downstream one. but we do not set any levee or ineffective flow area, so it is correct to have water still divided into two portions. This is an assumption that can be taken if you know better the situation of the river, the real physical characteristics. But let's see now if the water surface profile has changed with this mixed flow analysis. So let's open the profile using this button. This one. Okay. Now you can see we have much more cross-section. So also the definition of the profile is more precise, more accurate, and as you can see, this is the water surface and this is the critical elevation. In some points, the water surface is actually below the critical depth, so it is correct to have used the mixed flow hypothesis. You can also zoom in and see that, for example, here for sure, the water surface is below the critical ones. Of course, also, well, place here it's equal to the critical. Also, one is here is below, and you can also check this uh, looking at the tabular format output, which you can see clicking on this button with the tab with the table icon. For example, here you see for each cross section these hydraulic variables. There is the water surface elevation, which is shown in this column, and the critical water surface elevation. So, for example, you can see that in this cross section, the 10.250, which is one of the interpolated, you can easily recognize the interpolated cross section because they have a star after the revestation. For example, for this one, the water surface is below the critical water surface, and it is confirmed also by the Froude number, which is higher than 1. The Froude number is above 1 when the flow is rapid, is in a supercritical condition, while it's below 1 in the subcritical regime. Now let's see if some of the warnings we saw has disappeared. So we can go again with the view summary error warning notes. From here, we can see all the notes and warnings condensed in only one file. We see there are still some warnings. So the interpolation maybe was not enough to remove some of them. For example, the warning about the divided flow is still here because we actually do not put any other tool to prevent the division of the flow. But for example, okay, this changing in energy loss is still present, but the change of velocity has disappeared, for example, and now we have some note, the green ones, that inform us that supercritical flow started. Then we have an hydraulic jump. The hydraulic jump occurs when you switch from the supercritical to the subcritical conditions. So as you see, we have improved our geometry, but still some many warnings are still present in simulation. So in this case, it is up to us to evaluate if it's the case of improving and doing other changes in the geometry or select other options in the simulation. But this is some consideration that must be taken every time you make an hydraulic model, and you must evaluate the results when you check at the end of the simulation. So maybe one thing that can be done is try to repeat the cross-section interpolation with maximum distances that is lower. Maybe this can improve even more the results. But yeah, for now, this was, I think, an example uh, pretty complete to show you how to create and how to enter the flow data and the boundary conditions, and how to perform a steady flow analysis, and how to check the results and some suggestion, some evaluation that can be done in performing an hydraulic analysis. So for now, I think we're okay. We can stop if you don't have any question. If you have, please uh, tell me. You can both write in the chat, use your microphone. Okay, if there aren't any question and any problems, I think we can have a break and see you here again in an hour after the break lunch. So thank you for the participation until now, and let's see in an hour.